All right, so we're trying to maximize revenue in this situation, and we have to figure out how many yellow cakes and how many strawberry cakes should Jenny's Bakery make. And so for this optimization function, this z function, we need to figure out, well, if I'm trying to maximize my revenue, what kind of revenue do I make from each of the two types of cakes? So you look through the problem, and it says the yellow cake sells for $25, and revenue is, the money that you bring in. So when I sell it for 25, I would make $25 then for selling that cake. So I just write this as 25x. And then the strawberry cake sells for $35, so we would write that as plus 35y. So this is the z function. We just want to basically identify those values and then cross them out of the word problem so I don't accidentally use those again when writing my constraints, because the money that I make isn't a constraint, right? I don't want to be limited by how much money I can make. I want to make as most of it as possible. So then from here, the third part is writing those constraints. And I know this is the most challenging part of these problems. We've been working on this for a week now, on writing constraints. And the only way to get good at it is to try it. And if you don't get it, you keep on, if you fail, that's okay. If you don't find them all, that's all right. We're still working on it. But the more of these you do, the more you're able to see how these constraints work together and how you can identify them. And so we've got, I'm reading the problem, decorating and assembly time for a yellow cake is 2 hours, where the strawberry cake takes 3 hours, and there are a total of 450 hours that Jenny's Bakery can work. So that's another constraint there, right? The amount of hours that I have available to do this work. And some of the time I'm gonna spend making yellow cakes, some of the time I'm gonna spend making strawberry cakes. That total time together has to be, can I go over that 450 hours? No, right? That's all I have available. I can do less than that, or I can go exactly to that, but I couldn't go over the 450. That's all the hours we have in the bakery. So I'm going to make my first constraint saying, all right, so yellow cake takes 2 hours. So I would write that as 2x, because it's saying it's going to take me 2 hours for every yellow cake. Plus it takes me 3 hours for every strawberry cake, so 3y, right? 3 hours for every y, 3 hours for every strawberry cake that I make. And 2x plus 3y, that's going to represent all the hours that I'm spending making these cakes. And when I add up all those hours, it has to stay under this 450. It's got to be less than or equal to 450. Because those are all the hours that we have available. And then there's some more constraints. It says here, we need a minimum of 50 strawberry cakes. So just right off the bat, they need at least 50 strawberry cakes. That's why. So it's just saying that y has to be at least 50. And so the strange thing here, I know a lot of students read the word at least and they think less, because least kind of sounds like less. But if that's the least, that means if that's the lowest number, I've got to go over that number, right? I can't be under 50. I've got to have at least 50. So I could have 50, I could have 60, I could have 100, but 50 is that minimum number of strawberry cakes that we need to make in a given week, right? I've got some regular customers who always buy the strawberry cakes because they love them. And that's actually it. There's only 2 constraints here, right? Is there anything else? Any other constraints that I missed maybe? I think that's it, right? All right. And then step 4, we graph them. We identify those critical points. I'm not going to go over the whole graphing process right now. We should all be very, very familiar with that. But basically, when you graph this, you should have a feasible region that's going to be a triangle. And there are 3 different, oh no, I'm sorry. Yeah, 3 different critical points. Here, I've got that right here. Woo. Okay, so then in the feasible region, which I'm not going to go over the graphing right now, is you get these 3 critical points, and you plug each combination into the z function. Wait a minute, that's a different z function, isn't it? No, 25 and 35, that's it. So when I plug each of these 3 corners into the z function, I get these $3 amounts. And remember, the bakery is trying to maximize their revenue. And so I'm just looking at, well, which combination of the yellow cakes and strawberry cakes should I use to make the most money? And if I look right here, well, 5,500 is the most money that I can make. And that's at the coordinate 150, 50. And so that's my final answer. I should say, well, the bakery should make 150 yellow cakes and 50 strawberry cakes for a maximum revenue of $5,500. Did anyone else have this? Yes, yes, good, good, all right. Are there any questions from anyone else then on how I got these points? Or does anyone want me to actually go through the graphing and identifying those critical points, which I'm absolutely happy to do? Yeah, all right. I'll go through the graphing for one of them. All right. Okay, so I'm going to graph just the constraints in this case. So the things from step 3, you don't graph the z function, just those constraints. And so I want to rewrite this in slope-intercept form. So I'm going to subtract the 2x from both sides. That gives me 3y is less than or equal to 450 minus 2x. And then we would divide by 3 to get the y by itself. Y is less than or equal to 150 minus 2/3 x. And so then this in purple and this constraint in green, those are the only 2 constraints we have. And so we're going to graph this on the coordinate plane. And I look at my biggest value, I see 50 there, 150. So I want to scale my y-axis to make sure I get to 150. So I think I might go by 25s. You know, I don't want to do too small. If I go by hundreds, the whole graph will be just like right down here. I won't be able to see it too clearly. So I want to go by a value that I think would be kind of good. So I think by going by 25s, it should reach what I need nicely. So if this is 25, 50, and then 75, 100, 125, 150. And you can keep on going up to the top, but I know that I'm only going to need to get to 150 because that's the biggest y-intercept that I have here. And then we want to make sure we scale our x-axis by that same amount. Each line is going to represent 25 units. So then it's going to be 25, 50, 75, 100, 125, 150, 175, 200, 225, 250. All right, so there's our graph ready to be scaled for optimization. And I only have these 2 constraints to graph. So I've got y is greater than or equal to 50. Remember, if it's just a y and there's no x anywhere in the problem, that's going to be a horizontal line cutting through the y-axis right at 50. So I go to 50 on that y-axis, I put a dot, and we draw a horizontal line. It's going to be a solid line because it's that or equals to. And then greater than means you shade above. So I'm just going to draw a couple up arrows to represent the shading for that. I'd shade above this line. Then we just have that second constraint dealing with the number of hours we have available in the bakery. So I start at 150, put a dot. My slope is negative 2/3. So I go down 2, right 3, down 2, right 3, down 2, right 3. And there's going to be a solid line because it's an or equals to. And it says less than. That's a looks like a little L. So I remember, oh, that's a less than. That means below, underneath. Less than, less than, less than. And this is it for this problem. There are only those two constraints. And we want to shade in that, find that feasible region, which is where all the arrows are pointing. And I think most of you can see that this would be this section right here. So that is our feasible region. So you can shade inside. And then from here, you need to identify those critical points, which are just the corners of it, the vertices. And luckily, based on our scale, we actually can identify each of these really nicely without having to do like substitution or anything. And so we can see that our critical points going to be that one in the top left is 0, 150, 0, 50. And then this one down here, that's right at 150, 50. So then you just take each of those 3 points and plug them into that z function, right? That z equals 25x plus 35y. You're going to get 3 different dollar amounts. After that, you just pick the biggest one because Jenny wants to maximize the revenue from her bake shop. Are there any other questions on Jenny's Bakery? Or any questions from anyone at home either? Feel free to shout out. Okay, thank you.
Well, Jack.
Yeah, what's up, Carson?
So if I forgot, how do you get the answer if one of the points is not directly on like the center point of the line, like
Good.
those? Yeah.
Yeah, good question. So if you didn't choose a scale of like 25s or whatever magic combination I picked, how do you find the intersection point? Like, how would I know this exact coordinate? So if you didn't, if you can't identify it perfectly, if it were floating in the middle, something like this, right, where I can't be certain of the exact x and y value, what you need to do is write the equations of those two lines. Like if there's one line here, another line here, you'd have to write the equation of those two lines and then use like substitution or elimination or even Cramer's rule to identify that intersection point. So like for this point that we have in the lower right, I know that the equation for those two lines would be, write it out. So this horizontal line, I know has the value of y equals 50, because that's the constraint that I graphed. Y is greater than or equal to 50. So I'm just writing it as an equation because here, look, y is a 50. So this whole line is y equals 50. And I want to find where does that intersect this diagonal line right here. So I need the equation of this diagonal line also. And if I just go back to my constraints, the equation of this line was y equals 150 minus 2/3 x. So when you're trying to find the intersection point, one of those critical points of these two lines, just write them out like a system of equations, and then you can use substitution or elimination or Cramer's rule to find out, well, what is that x and y combo? Now, if these were my two equations that I wanted you to solve, which, hey, you're gonna have to do this on the test today, right? Show substitution and elimination and Cramer's rule and all that. In this case, since y is equal to 50, I would just take that value and plug it into the other equation for y. So this is the substitution method. And so I'd say, okay, so 50 equals 150 minus 2/3 x. And all we're going to do is solve this equation for x. From here, I would subtract 150 from both sides and get negative 100 equals negative 2/3 x. From here, if I have just one term on the left side and one term on the right side, and they're both negatives, I know I could just divide by a -1, which basically flips the sign and makes them both positives. So this is the same as saying, hey, 100 equals positive 2/3 x. Then my last step would be to cancel out the fraction, which all you need to do is multiply by the reciprocal. So you flip that fraction upside down. You do that on the left side, and then you have to do it on the right side to keep the equation balanced so that those cross off. Over on the left side, to multiply a number. Oh, I dropped the pen. My Spidey skills are not working today. Don't have my sticky fingers on. 3 times 100 is 300. Divided by 2 equals 150. And so here I see that 150 is x. And if we look back up here, 50 was y. So I have the coordinate 150, 50. And that's how I got this point right here. See 150, 50, except I could see that point on my graph in this scenario. I was able to see it right at the intersection point. But if it's not, you would just use one of the other techniques for solving a system of equations. Other questions from anyone here or at home? Okay, I'm just going to go through the first few steps of these last two. So Superbats Inc. makes two different types of bats, the wallbanger and the dingbat. So X equals wallbanger. And the Y is going to be the dingbat. These are two different types of baseball bats. Two is to write my Z function. And I just kind of look at the question word typically is always going to tell me what I'm trying to optimize. I look for the word maximize or minimize, and it says it right there. We're trying to maximize profit. So that's how I know what goes into my Z function. I need to figure out the profit from my X and the profit from my Y. If you just read the problem, it tells you that this bat has a profit of 17, and that's the wallbanger it's referring to. So the wallbanger has a profit of $17. So I'd write that as 17x. Plus, I'm looking for the profit of the other bat. All right, so the dingbat profit is $29. So I'm going to write that as 29y. 17x plus 29y. That's going to be my Z function. That's what I'm going to figure out my profit. I'm going to try to maximize. And then we've got our constraints. So let's cross off those dollar amounts so that I don't accidentally write a constraint with those. And it says that this wallbanger takes 8 hours to trim and turn on the lathe, where the dingbat takes 5 hours to trim and turn on the lathe, and the maximum time available on the lathe is 80 hours. So I know that that's going to be one of my constraints. In my baseball bat shop, I've got this tool called a lathe that helps me trim and turn the bat, basically like spin it really fast and get the shape that I want. And each of the two bats take a different number of hours, and there's this total amount of 80 hours on this machine. This is called the lathe. And so if it takes me 8 hours on the lathe for every wallbanger, I'd write that as 8x plus 5 hours on the lathe for each dingbat. Then all that time that I'm spending on the lathe with these two different types of bats can't go over that 80 because I only have 80 available hours. So this has to be less than or equal to 80. So that's like taking a big block of wood and basically getting it into the shape of the baseball bat that I want. And then my next constraint is the hours to finish the product. So basically polishing it up, sanding it, staining it, making it look super nice and fancy. And so that wall banger takes 2 hours to finish. The dingbat takes 5 hours to finish, and I only have a maximum of 50 hours for finishing. So that right there is my second constraint. So 2 hours to finish a wall banger, so that's going to be 2x, plus 5 hours to finish the dingbat, so plus 5y, and I only have 50 hours for finishing altogether, so that's got to be less than or equal to 50. So those are your constraints. From here, I know all of you can do this. You would rewrite these in slope-intercept form, right? Get them in y. You'd graph them. There's only 2 lines in this case, 2 diagonal lines, and you'd find those intersection points. And for this one, you get 3 intersection points. So that's right here. Right there, my constraints for wall banger and dingbat. This is my z function, the profit I make for each of the 2 types of bats. And I'd get these 3 intersection points, 0, 10, 5, 8, 10, 0. And you can see I'm trying to maximize my profit. Well, obviously 317 is the most money that I can make. And that's at the coordinate 5, 8. So then I just had to interpret that answer and say, oh, okay, well, 5, that was my x, that was wall bangers. So we should make 5 wall bangers. And 8 was the number of dingbats, so we should make 8 dingbats, and we'll get a maximum daily profit of $317. So this one would be a good situation where you'd have to solve this as a system of equations to find that intersection point, that 5, 8. Or actually, if you scale your axes by tens, you'd be able to see it pretty clearly. Any questions on writing the z function or the constraints for this problem? Okay, let's look at the last problem real quick. And this will be it for today. So I've got a parking area and a big parking lot. And a car requires 6 square meters and a bus requires 30 square meters. So I can kind of see that I've got 2 different types of vehicles. I've got cars and I've got buses. And it says how many of each type of vehicle. So what are how many of the 2 types of vehicles? That is going to be my 2 variables, my x and y. So x equals the number of cars. Y equals the number of buses. That does not look like a U. Buses. 2 is my z function. What am I trying to optimize? Again, look at the question in that word problem. Usually it's right at the end. We're trying to, there's the word maximum. That's what we got to look for these optimization problems. Maximize or minimize. We're trying to maximize the income. So what's the income that I get from a car? Can you guys see in the word problem? $250. That's how much I make for cars. So we'd write 2.5x plus the income from a bus. It's right next to it. $750 for buses. So 7.5y. That's my z function. So we don't graph this. This is what we use in the last step to plug in those x and y values. Now writing constraints. So I've got 600 square meters available in my parking lot. Right, that's like how much space I have to park vehicles. Some of these vehicles are cars, some are buses. So let's find what's the square footage for each of those vehicles separately. And it says right here that the car requires 6 square meters. So I'd write that as 6x, right? 6 square meters for every x, 6 square meters for every car. The bus takes 30 square meters. So that's the amount of space for every bus. So I'm going to add 30y. So that's the amount of space coming from cars, the amount of space coming from buses. And when I add up all the space that those vehicles are taking up, I can't obviously take up more space than the parking lot has available. So I've got to be less than or equal to this 600 total available square meters. All right, so I've used the 30, the 600, the 250, the 750, the 6. So if there are still numbers in the problem, basically that means there's probably still some constraints for us to write. And I see that it can handle no more than 60 total vehicles. Now, does that say whether those vehicles are cars or buses? It's just all together, right? So when I add up all my cars and buses, I can't have more than 60 of them. So we're just going to write straight up x plus y, because x is just the number of cars, y is just the number of buses. When I add those numbers together, I can't go over 60. So I've got to be less than 60 or equal to 60, right? I could equal that amount exactly. So that 60 is used, and then there's one more number I see, and it says a maximum of 15 buses. All right, so that's one more constraint. I can't have more than 15 buses in my lot. I could have less than 15 buses, right? That's the maximum. So my number of buses, y, it's got to stay under that 15 or equal to 15. So y has got to be less than or equal to 15. And that's going to represent my last constraint. If I look back in the problem, we use all the numbers. There's nothing else in that word problem that says what we're limited by. We do technically have those 0 constraints. Obviously, we can't have -2 cars and -5 buses, but that just tells us we're going to be in that first quadrant on the coordinate plane. Questions on any of those constraints? So we'd solve both of these for y, right? Subtract 6x, divide by 30. Here, just subtract x. And when we graph them, this time. So you get these 4 intersection points on the graph. And if you plug each one of these ordered pairs into our z function, you get different dollar amounts. And we're trying to maximize the income that we get from parking vehicles. And so right here, I see that the biggest number is $200. And I get that from this coordinate, 50, 10. And so just, well, what does that 50, 10 mean? Remember, x was the number of cars, y was the number of buses. And so then the attendant should accept 50 cars and 10 buses to get that maximum income of $200. Any questions on any of these? For anyone here or anyone at home? If you have any more questions. Okay, so we're not going to move on and learn anything new. We still need to practice this, obviously, okay? Looks like maybe 3 of you actually did this, so let's try to, do this ourselves from now on. Your next assignment then is, for those of you at home, what I want you to work on before you come to class on Wednesday is if you go to our calendar, click on Continue Linear Programming, and there's a worksheet linked out here for you. And this worksheet is going to look familiar to you. For those of you here, I've got a copy for you that you can have after the test. And so I've got 6 more linear programming problems. And hey, look at this first one. A baker makes bran muffins and corn muffins. Wait, does that sound familiar at all to anybody? The grossest type of muffins available? Didn't we talk about this already? So these are the same problems that we went through for your lesson a week ago when we first learned about writing constraints. And so I'm using those same exact word problems. So just grab these notes from a week ago and you're already halfway done because you already have your variables defined. You already have your constraints. And so the next thing you have to do is identify the optimization function, right? What's the Z function? Like down here, maximizing profit. So I added some more words to the word problem basically. And then you have to graph it, the constraints, identify those critical points, and plug them into the Z function, okay? So this is now practicing the second half of linear programming. You already did the first half, writing the constraints. Now this is the rest of it, graphing, finding those critical points, and then identifying the answer, the maximum or the minimum. So what I want you to do, for those of you at home, if you still have this sheet from last week, hopefully you should, with the constraints written on it. You can grab that, and then I want you for your homework for Wednesday for everybody is basically write the Z function. Okay, what are you trying to maximize or minimize? Graph it. You can graph it just on the graph paper I gave you, or if you need more, let me know. And then test those points in the Z function and answer the questions. That's what I'm looking for this one, all right? Now, you absolutely need to practice this, okay, everybody? It looks like here in the classroom, a lot of you did not do this at all, and you just kind of followed along, and I saw you rushing to write everything that I just showed you today. If that's what you did, you're not going to learn anything, okay? You've got to try this on your own to learn. You will be tested on this, and if all you're doing is waiting for me to go over it, you're not going to learn, okay? You need to learn. You need to put in the work and take your time yourself, okay? So, for everyone at home, that's all I got for you. You can sign off and just email me if you do get stuck on any of these questions before Wednesday, and I will help you out as best I can, but definitely give it a fair shot, okay? Otherwise, I will talk to you all later.
Thank you.
You're welcome.
See ya.
See ya.